Anyway, today, it's a great pleasure for me to welcome today's speaker, who is Professor Jim Evans of the Department of Physics in the University of Puget Sound in Washington, in the United States, where he's an emeritus professor. And I'm glad to say that there are no tariffs to pay on importing people, not yet. Anyway, Jim is a historian of science. His specialities include the history of cosmology, and my notes keep moving, and ancient Greek astronomy. He's the author of The History and Practice of Ancient Astronomy and of numerous research articles. And he's the editor-in-chief of the Journal of the History of Astronomy. And he's going to talk to us today, as it says up there, about the material culture of ancient Greek and Roman astronomy. Jim, over to you.
Thank you. It's a pleasure to be here with you today. In our day, there isn't any one central science. Science is divided into dozens of specialties and hundreds of subspecialties. But in the ancient world, there was a central science, and it was astronomy. It had important links to mathematics, to philosophy, to religion, medicine, you name it. The material manifestations of astronomy are vast. And what I'd like to do today is to show you some of this very rich culture of material objects that represented either practical astronomical tools or symbolic uses of astronomy. Geminus was a Greek mathematical and astronomical writer who lived in the 1st century before our era. He was the author of a introduction to astronomy, kind of popular work. But he also wrote a separate work about the branches of mathematical learning. And in his treatise on the organization of the sciences, he divides, first of all, between the pure and the applied. On the pure side, we have arts like arithmetic and geometry, dealing with mental objects only. And on the physical side, he divides, first of all, into 6 or so major branches, things like practical calculation, what the Greeks called logistic, geodesy, harmonics, the structure of the musical scale and the way it's related to arithmetic, optics, and so on. Under mechanics, we have things such as military engineering, but also the art of wonderworking. This was the art of making a machine that would amaze and inspire the observer. A lot of these devices are described by Hero of Alexandria in his Mechanica. One of my favorites is a mechanical toy temple. You light a little fire on the temple altar, and through a network of hidden pipes involving steam pressure and so on, a mechanical god comes out and accepts the offering. But under this same art of mechanics, we have, in fact, something that will be of interest to our subject, sphere making, the art of building images of the cosmos. These could be such things as simple celestial spheres, but it also includes things like gearwork mechanisms to replicate the motions of the planets, something like the Antikythera mechanism. And astronomy, one of the 6 main branches of applied mechanical learning. And here we have a range of subjects of interest to us: mnemonics, the theory of sundials, meteoroscopy, specialized observing instruments like armillary spheres, and dioptrics. We'll come back to each of these arts in just a bit. Let's look at sphiropoeia, or the making of spherical models of the cosmos. This is a nice coin from Roman Bithynia, which represents Hipparchus seated at a table before a celestial globe. Hipparchus was one of the most accomplished of the ancient Greek astronomers, and there's no way to imagine that this really represents it the way he looked, because the coin is minted centuries after his lifetime, but it's a nice thought. The most impressive spherical globe that we possess is the Farnese globe held by Atlas. It's now in the National Archaeological Museum in Naples. It was excavated from a ruin in the Renaissance, and only the torso, head, and globe were still there. The arms and legs are all modern reconstructions. But here we can see Atlas holding up the globe, the spherical globe of the cosmos. In this modern reconstruction, we can see how it works. You can see the system of parallels, which represent the Arctic Circle, the tropics of Cancer and Capricorn, the equator, and then slanted, the triple belt of the zodiac. So the middle one is what the Greeks called the circle through the middles of the signs. We would call it the ecliptic. And it's supposed to be 12 degrees wide, this whole band, to encompass the latitudinal wanderings of the planets in the course of their daily and annual motions. The ultimate source for these globes was a work by Eudoxus of Cnidus called The Phenomena. It doesn't survive, but it inspired a poet, Aratus, to write a versified version of The Phenomena in the 3rd century BCE or so at the court of the king of Macedon. So in Aratus, we have a good example of what the lost work of Eudoxus must have consisted in. As far as we know, this was the first complete Greek description of the celestial sphere. So part of the work tells you where the constellations are in relation to each other, which ones lie on the Tropic of Capricorn, which ones lie on the celestial equator, and so on. The Greeks tended to paint their statuary, and so we could imagine that this modern replica looks the way the Farnese globe would originally have looked with the sky painted. A much smaller globe which came to light really on the last couple of decades, is in Mainz in Germany. It's about this size, and from the square and round holes at the top, it seems likely that it was originally intended to be placed at the tip of a vertical gnomon. So it's kind of an image of the cosmos for a garden sundial display in which the globe serves as the shadow caster or gnomon. A closely related instrument is the armillary sphere, which the Greeks called a sphere krikote. No real examples of these survive, but we have lots of examples in statuary and verbal descriptions of them. In the case of an armillary sphere, instead of a complete globe, you have it represented by a kind of set of bracelets or armbands, a kind of skeleton sphere that emphasizes the most important circles, the tropics, the equator, and ecliptic, and so on. A spectacular example comes from Stabiae, one of the suburbs of Pompeii. It was a ceiling painting, and we could see what was probably intended to be an armillary sphere. But an even more striking example is a mosaic in the Casa de Leda in Salunto on Sicily. Here you can see the Earth in the middle and surrounded by a horizon ring, and then the parallel circles of the tropics and equator and the slanted circle of the zodiac. These spheres appear also in lots of artwork. And there are examples of mosaics showing a philosopher teaching about astronomy, but pointing to a globe. Like the kind of work that would be very familiar to most observers. Let's turn now to mnemonics, or the science of making sundials. And here we can see a nice mosaic from Trier with a philosopher with a sundial. Vitruvius, the writer on architecture from the beginning of our era, lived in the reign of Augustus. He wrote a book called On Architecture, divided into 10 different books. The 9th book is mainly devoted to astronomy because an architect might be in need of astronomical techniques. For example, in just establishing the principal directions for laying out streets and so on. And Vitruvius also spends a section of his chapter 9 on the kinds of sundials. So he gives us a list of dials and their inventors. He doesn't go into a lot of detail, but from this we can imagine there must have been a specialized body of short astronomical works describing the invention and construction of different types of dials. And most of this work has disappeared, and we have to reconstruct the history from the surprising variety of surviving sundials. For most of Greek and Roman technology, very little in the way of material objects survives. We mostly know about things from the texts that have survived. The sundials are the one big example. There are about 600 surviving sundials from Greek and Roman times, showing an astonishing variety of types. So it was a very rich part of the material culture of astronomy. The simplest dial in principle is a kind of hemispherical dial with a hemisphere carved out of the stone, and then a gnomon, shadowcaster, usually of bronze or iron, inserted anywhere. But the important thing is that the tip of the gnomon be located at the center of the sphere. This dial is the easiest of all to understand because it's kind of an inverted image of the sphere of the heaven. So you can imagine when the sun is located at a certain place in the sky, projecting a ray through the tip of the gnomon, the projected point on the surface of the dial is the point that corresponds to that point on the celestial sphere. Of course, to make a whole hemisphere would be tedious stoneworking and kind of impractical. It would fill up with rainwater. Luckily, you don't need an entire hemisphere because the sun can't be found at just any old place in the sky. It's always got to be between the two belts of the Tropic of Cancer and Tropic of Capricorn. So it's possible to cut away the south face, and you could leave the dial open so rainwater can run out. The Greeks divided the day into 12 hours. So every day is 12 hours by definition, from sunrise to sunset. In the summertime, the hours are longer, and in the wintertime, they're shorter. We have an expression that survives in English that reflects this old way of time reckoning. We talk about doing something at the 11th hour. Well, the day's almost over, right? It's only 12 hours long. The kind of hour we use today, the equinoctial hour, in which the whole day and night is divided into 24 parts, was known to the ancient Greeks, and the astronomers used it when they needed a technically constant interval of time for doing astronomical calculations. But in everyday life, it's this seasonal hour that's always used. Of all the hundreds of dials that survive, they're all, except maybe one or two, divided into these seasonal hours that change in length with the seasons. Here's a nice example from Pompeii about this size. The place where the gnomon would have been inserted is broken away at the top. Another kind of closely related dial is the conical dial. Here, the shadow receiving surface, instead of being a hemisphere, is part of a cone. So you could imagine rolling up a piece of paper into a conical shape, and then you can use any angle of opening that you like for the cone. But when you mount the thing, the axis has to point at the north celestial pole. And the theory of these is just slightly more complicated because the shadow lines have to be projected onto a conical surface rather than to the spherical surface of the hemispherical dial. Here's one from Greek Alexandria. You can see the hour lines are straight lines along the surface of the cone. You could see the circles that represent the two tropics and the equator. Unusually, this dial has its hours numbered. The Greeks used letters of the alphabet for numbers. Alpha, beta, gamma were 1, 2, and 3. And very few dials actually have the numbers engraved. So this is a nice example. This is a dial that I recently reassembled, working with Marcel Moret and the Egyptian collection at the British Museum. It was excavated from Tanis in Greek Egypt at the early part of the 20th century. But it was in a temple that had burned, and the dial, it's a small dial made of hippopotamus ivory, burned, and so made very fragile, and it was broken in dozens of pieces when it was found. And Marcel and I were able to put it back together, and we discovered an interesting feature of this dial. It's the usual sort of conical dial with the 11-hour lines engraved on the conical surface, and then the circles that represent the beginnings of zodiac signs. But there was also an inscription on the cutaway south face. Now, typically, these are cut away to correspond to the latitude of the place of observation. And the reason for this became clear from the label here. It's a Greek word for equinox, Maria. So with a dial of this sort, the cutaway face is parallel to the plane of the celestial equator. And so in the summer and spring, all through the course of the day and night, the sun never shines on the cutaway face. At equinox, when the sun moves to the southern part of the sphere, suddenly that face for the first time is lit up by the sun. So besides telling you the time of day, this also is an equinox indicator. It indicates when the spring and fall equinox occurs by the lighting of this one slanted face. There are dozens and dozens of dials with this feature, but so far this is the only one that's come to light with an actual label showing that that's what it was really meant to represent. Here's an example of a plane dial, which you constructed on a horizontal surface, and you has to be lined up so the meridian is north-south. And these have this characteristic batwing shape. The black dot just above the upper curve there is where the gnomon would have stood. It would have been upright, made of iron or bronze or something. And the curved track that goes like this is the track that the shadow tip will follow in the course of the day on summer solstice. And then the straight line across is the shadow track for equinox. And then the lower curve is the shadow track on winter solstice. And the characteristic batwing shape with the hours that's readily apparent. And around the outside, we have the names of 8 winds engraved in Greek. Even though this dial was found in Italy, Greek was sort of the international language of science. And so there are examples of astronomical artifacts found in the Roman world, but engraved in Greek. It kind of served the kind of purpose that Latin served in the Middle Ages, a kind of international language of science. So these winds were personifications of winds. Each wind has a god, which is its chief sponsor and gives it its name. Each wind was deemed to have particular qualities and to blow at particular times of year. But these wind names are also used as direction signs. So Boreas is the direction of the north wind. Zephyrus is the west wind, and so on. So these are used as wind gods, but also as winds with meteorological properties, and also as just direction signs. There are also some dials of fantastic artistic qualities. This is an example of a dial found in Roman Carthage. You can see it's a good-sized thing, and it's made in the shape of a drinking cup, decorated on the outside with leaves and acorns and things like that. And the way it works is it's a pierced ceiling dial. So there's a small hole in the top through which the sunlight passes, and then the spot of light gives you the hour by where the spot is located among the hour curves. So a lot more going on here than just mere practical time telling, right? It's a way to show off your skill as a geometer and collaborate with an artist to make something impressive. So we've talked a little bit about spheropoeia, the making of spherical images of the cosmos, and a little bit about mnemonics, the art of sundialing. So I'd like to say a little bit about how closely connected these two arts are. So I mentioned Vitruvius's on architecture, in which he mentions a drawing which is used for laying out a sundial. And you can see that it's a kind of side view of an armillary sphere with some of the circles folded down into the plane of the drawing. Vitruvius tells us that he's not going to go into a lot of detail because he doesn't want to become tiresome by writing too much. But just when he gets to the good bit, which would be explain how you actually lay out a sundial from this geometrical drawing, he stops. So we have to reconstruct the way the last bits of the projection work. And he tells us if you want to know more, you can find how these projections work if you look at the writers on the subject. So this is one of the ways that we know that there were a bunch of short treatises by different writers about, hey, I've invented a new kind of sundial. Here's how the projection works. Provided, Vitruvius says, you understand the figure of the analemma. So this analemma, the Greek word also means something like scaffolding. So it's a preliminary construction that you make to help you make the main thing, which is the sundial. And you can see by comparing them side by side, the analemma is a kind of side view of an armillary sphere. You could see for the people in the live audience, you could see the horizon, which corresponds to this Renaissance armillary globe with a horizon plane, the axis of the universe, the slanted equator and tropic circles. And then the Tropic of Capricorn has been bent down into the plane of the drawing. So you imagine that in the working sphere, this dashed circle would be bent out at right angles to the plane of the diagram. And a number of writers have shown how you can project a sundial by just making geometrical projections inside the analemma. So we have good understanding of how the dialers went about doing this. So a lot of them probably worked from the geometrical projection method. And we can see that there's an enormous range of quality in the surviving sundials. Some of them are rather crude and sloppy. Others are exquisitely and accurately done. Or you, instead of projecting, you could use the diagram as a basis for doing a geometrical calculation. And no doubt, most of them were just projected by hand. Vitruvius also tells us there were dials meant for travelers that you could carry around. The great majority of the surviving dials, hundreds and hundreds of them, are of stone, pretty indestructible. Here's a nice example of what today is sometimes called a shepherd's dial. There's a gnomon, which can be put inside for when you're traveling, but then you take it out and put it on top. And then you have to orient the gnomon so that it stands over the line that represents the correct month of the year. And then the sequence of hour curves allow you to read off the hour by where the tip of the shadow falls. I should mention, when you're telling time, you point the dial right at the sun. And so basically it's an altitude dial. It tells you the hour by the altitude of the sun. This is a rather sophisticated portable dial. Most of them are about this size. There are quite a few of them known. You have a rotatable vane, which you set for the month of the year. An outer scale is adjusted for your latitude. And then the hours of the day are actually engraved along the curved surface of the rotatable vane. And in using it, you turn the dial so that the shadow of the shadow casting gnomon, this horizontal stub, falls right along the dial. And then you can read the hour there. So you can see a rich variety. There's quite an interesting dial in the Museum of Sir John Soane. It's in Lincoln's Inn, which has just only recently been well understood. It's a dial that was discovered in Italy at Tor Paterno around 1781 or so. Eventually, the dial wound up in England. And so by the 1820s, it was in Sir John Soane's museum. He traveled a bit collecting and built, by joining three existing buildings together at Lincoln's Inn, he was able to get a larger storage space to display his collection. And so that it's still there. He was granted a perpetual funding by an act of parliament, provided that the museum always remained free of charge to the public. And I'm happy to note that the custom is still observed today. So this dial was kind of a mystery because it seems to tell time in modern equinoctial hours. You can see it's a statue of Atlas holding up the celestial globe, but the globe has been inverted and it becomes a hollow sphere for dialing rather than a normal closed celestial globe. And the axis of the sphere corresponds to the elevation of the axis at the fine spot. So it's well made for the place for which it was found, just outside of Rome. The tricky bit is that it tells time in modern equinoctial hours. This shouldn't exist because there are no ancient dials that do this among the hundreds and hundreds of others. So either there's something odd going on, or else it was an almost unique piece from Roman antiquity. The solution of the mystery becomes clear when you take a look at the dial in its complexity from the side. You can see that there we go. Somebody cemented a wedge of stone underneath the base to tilt the whole thing forward. This basically changes the effective latitude for which the dial is supposed to function. And so, in fact, we can also see that in this view that let's see if we get this to, well, we can see that the end cap is a separate piece. So originally the shape was of this. The cap at the top at the north celestial pole has been added later. So this was a Atlas dial that originally told time in seasonal hours, the 12 equal hours from sunrise to sunset. But sometime between 1781 and the 1820s, somebody converted it into a dial that tells time in modern equinoctial hours. This was done by adding the cap to the North Pole region and by tilting the whole thing by an appropriate amount to make the dial suitable for the latitude of the fine spot. So this is a kind of time conversion, same sundial used in two different ages, telling two completely different kinds of time. I'd like to turn now to the making of cosmological models. Well, we've seen a good example of a cosmological model, which was the image of the whole celestial sphere, which could be engraved in metal or in stone. And the tradition goes way back. In the Republic of Plato, at the very end, there's a kind of cosmic vision. There's a hero named Er who dies on the field of battle. But 10 days and nights, his body lies on the ground and doesn't decay. And his friends and companions are amazed when, at the end of the 10th day, he comes back to life. And then he tells his friends a story, something that he saw when he was out of this world. He says he saw a woman spinning thread. So this is a nice example of a vase from the collection at the British Museum, showing a woman spinning thread. So the glob of raw wool is put on the tip of the distaff, and she's pulling out the yarn, making the yarn with her fingers. So as you kind of twist it as you pull it out. But the yarn is attached to a spindle whorl. Well, you can see with a little hook and a ball that gives it some weight. And it's the spinning of this that helps her in the making of the yarn. So you can imagine clothing was expensive then, right? You start this way by starting from raw wool, making your own yarn. Well, Plato tells us that his hero saw a cosmic vision when he was out of this life. He saw the spindle of necessity. So anake is the Greek word for necessity. And here she's personified as a cosmic being. She's spinning yarn, but the spindle whorl that she's using, instead of just being a glob of stone, it's actually made like 8 little spherical shells nested one inside the other. And Plato says it's like those boxes you can get, but we would think of maybe Russian dolls with one nested inside the other. So there are 8 of them that represent the sphere of the fixed stars, and then the spheres that carry the individual planets, the sun and the moon. And so the daily spinning of the globe, represents the motion that makes day and night. But then inside, each of the spheres is carrying a single planet. And these go in the opposite direction, each in its own period. Mars takes about 2 years to go around the zodiac. Jupiter takes about 12 years, Saturn about 30. And then ranged around the outside are 3 daughters of necessity. They're the Fates, Atropos, Clotho, and Lachesis. So one of them with her right hand helps the daily westward motion. One of them with her left hand helps the planetary zodiacal motion in the opposite direction. And one of them working with her left and her right hand helps produce the forward and retrograde motions of the planets. So you could see that in this poetic vision, we have a sort of model of the working of the cosmos. It's in poetic language in Plato. But there was a philosopher, Theon of Smyrna, who lived in the 2nd century of our era, who tells us in his introduction to astronomy that he made one of these. So there's a nice example of a cosmic model made after the passage in the Republic of Plato, made by Theon. It's very rare for us to actually know what any particular ancient scientist looked like. We do have these fictionalized portraits of Euclid and things like that, but they're centuries after the time. This bust was found at Smyrna, Theon's hometown, and the inscription in the base says it was dedicated by his son, and it represents Theon, the Platonic philosopher. So this is a guy who wrote a book called On Knowledge Useful for Reading Plato. It's a kind of introduction to the 5 mathematical arts: arithmetic, geometry, astronomy, and music theory, and so on. And the astronomical chapter is one of the more philosophically inclined introductions to astronomy that have come down to us. But that's no doubt what he really looked like. Another kind of cosmological model is a kind of geared calculating instrument. This is a nice example from Byzantine times. It's a smallish object about this size. It doesn't survive complete, but we do have several of the gear wheels that went with it. One of them is the oldest known ratchet, which was intended to keep you from turning the dial backwards in the wrong direction. So the tooth wheel has numbers of the month, days of the month engraved around the outside. And this is the ratchet, which keeps you from turning the thing backward. This is a reconstruction by Michael Wright at the Science Museum, showing you what the thing would have looked like. So it contains one of those portable sundials that I showed you before, with the curved vane that has to be rotated for the correct month of the year, and the outer scale, which has to be adjusted for the user's latitude. But then there must have been a dial with the days of the week, represented by the planetary gods for which the days are named. So click it along one day at a time. And then on the back, there was a thing which showed you the changing phase of the moon as you click it notch by notch. So quite a nice example of an instrument that starts with a practical sundial, but it's carried far beyond what it needs to be. It's a bit like a Fitbit, more than you need. Whoops. And of course, the most impressive surviving ancient cosmological model is the Antikythera mechanism. I'm almost certain that almost everybody has heard of this. If you've heard of the Antikythera mechanism, you could, yes? Yeah. So originally it must have contained something like 70 gears or so. About half of those survive. It was about the size of a shoebox with a wooden case, but bronze metal parts. And when you turned a crank, there were pointers that went around representing the motions of the sun and moon and planets around the zodiac. And also a turning ball that represented the phases of the moon, one half of it silver and one half of it black. So as it rotated around, you could see the changing face of the moon. Again, a kind of a cosmos in a shoebox, summarizing everything that anybody knew about the way the universe worked at the time. So something well beyond what you would need for any kind of practical application, but a really sort of a tour de force of applied astronomy, mathematics, and mechanical engineering. In the little bit of time we have left, I'd like to turn now to dioptrics and meteoroscopy, two of the classic branches of instrument making that Gimenez referred to in his classification of the mathematical arts. An instrument called a dioptra was used already by Archimedes to try to measure the angular diameter of the moon. And other versions of it were made and used by Hipparchus and by Ptolemy. Here's the basic idea. You have a long-armed instrument. Hipparchus's must have been 6 feet long or so. Probably Archimedes was much shorter. At the end, there's this plaque with those points H and P. So at H, there's a small hole. You aim that at the sun, for example. And then you have this cylinder C, which can be slid back and forth in the groove. And what you want to do is when you say, look at the moon, you put your eye near the right end of the instrument. And you're going to aim the cylinder at the moon. You look through the small hole, and you want to move the cylinder in and out until the cylinder just barely covers the moon. Right? So you're looking through the tiny peephole, you let the cylinder just barely cover the moon. If you were looking at the sun, you wouldn't want to look at it directly with your eye, but you use it in some sort of indirect way. And the point of this is to be able to measure how many degrees big the moon or the sun are in the sky. They're about half a degree. And that turns out to be something important in the ancient methods for trying to estimate the actual size in miles or stades of the moon or sun. Another classic instrument is a quadrant, which could be made of bronze in the form of a ring, or could be engraved on a block of wood or stone. And here you have these two horizontal pegs, which are going to cast shadows. You need to aim the block so that it runs north and south on your meridian. And the quarter circle from C to E is divided into 90 degrees. And Ptolemy tells us in his description of the instrument that you can use a plumb bob at the ends of these pegs to make sure everything's lined up nice and vertical. And you can use this to measure then the altitude of the sun at noon. How many degrees above the horizon is the sun? You do it using the shadow cast by that horizontal gnomon A. So one of the most important parameters in ancient astronomy is what's called the obliquity of the ecliptic, the angle between the equator and the zodiac. To get this, you would measure the altitude of the noon sun at winter time when the sun is lowest in the sky, and then at summer when the sun's highest in the sky. And then the difference between the two tells you how many degrees north or south the sun shifts as you go from midsummer to midwinter. And half of that number is the obliquity of the ecliptic, the angle between the equator and the ecliptic. So this instrument could be used to try to estimate the day and time at which a solstice arrived, when the sun was highest in the sky. But the sun changes its altitude so slowly around the solstices, it'd be difficult to get a very accurate measurement. So more useful were often measurement of equinoxes. And by measuring an equinox, I mean to measure the day and, if you can, the hour of the day at which the equinox occurs. Because one good way to measure the time of year, the length of the year, is to measure an equinox and then measure another one 150 years later. And you do this by looking at the records left by your predecessors and then measuring your own equinox. So Ptolemy describes an instrument which is a ring, which has to be placed in the plane of the celestial equator. So that means the angle the ring makes with the ground has to be equal to your co-latitude, 90 degrees minus your latitude. And then things got to be oriented so that it's face onto the zodiac, onto the equator. So the way this works is that when the sun is on the celestial equator, moving along the zodiac, it finally reaches the celestial equator. And at that moment, the shadow of the upper part of the ring will fall onto the lower part of the ring. So at that one moment, you can sense when the sun is accurately in the plane of the celestial equator. And so you try to determine, again, not only the day at which the equinox occurs, but also the hour of the day if you can. It can be tricky. Ptolemy tells us there were two of these rings in one of the squares in Alexandria, but one of them was defective because it seemed to indicate two different equinoxes, one a day later or a few hours later. So maybe one of the rings was warped, or maybe it had shifted a little bit. We don't know for sure. Oh, here's an image that shows again a little bit about how this works. So you can see the daily motion of the sun in the spring or summer. It travels on a circle parallel to the equator, but north of the equator. And in fall or winter, it's always south of the equator. Only at the moment of equinox, when the sun is in the plane of the equator, can the shadow of the upper part of the ring fall on the lower part. Ptolemy describes a much more complex ringed instrument consisting of 9 rings. And this apparently he used for measuring positions of the planets along the zodiac. None of these have survived. We have basically his written description of them in the Almagest, and then in commentaries by later writers such as Proclus and Theon of Alexandria. I'd like to mention also briefly in the astrolabe and related instruments. The astrolabe is kind of the emblematic astronomical device of the Renaissance and Middle Ages. It's a kind of celestial globe or umbellary sphere that's been flattened into a plane. There's an underlying network of lines that represent the degrees above the horizon and degrees around the horizon, and then a ring with teeth on it that indicate the locations of individual stars. It's called the rete. And so that's the celestial sphere with its star pointers. And you could solve all kinds of practical problems. You can use it to tell time in the daytime or the nighttime, dozens of different applications. This is based on a different kind of projection than we use for making sundials, but a kind of projection known as stereographic projection. This instrument, the astrolabe, is also closely related to a kind of water clock called the anaphoric clock. Now, these are described by Vitruvius also in the works on architecture. And the way fragments of two of them have been found. The most spectacular was at Salzburg in Austria. So the original sky plate was about this size on the Salzburg instrument. And you can see it was engraved with figures of the constellations. But around the zodiac were drilled holes, 365 of them. And somebody had the job of taking a peg to represent the sun and moving it along from hole to hole. And then the whole disk was turned by a water clock. So the disk would go around once in a day and a night. The zodiac has broken away along the engraved line of holes. It's like the paper towel that's ripped away at the place where so you can see along the lower boundary, the sort of jagged edge, that's where the zodiac ring has broken away. But you can see part of the constellation of Aries, the ram, and the Pisces, the fishes, just to the right. So again, a device that goes well beyond anything needed for practical time telling, but it's a kind of tour de force of the mechanics art. It embodies astronomical learning, but also mechanics and art as well. One of the most prominent ways in which astronomical learning was displayed was in the connection with astrology. Now, astrology isn't really all that old. There are ancient works that tell us it went back tens of thousands of years, but it's all just made up because they were fond of spinning stories about the antiquity of their art. It starts really in ancient Babylonia around 400 BCE or so. There are many other kinds of divination, but in Babylonia, the planetary gods really only cared about the king. The planets would give messages that the king's priests would interpret and write on clay tablets and send them to the king. The important things were like, is there going to be a good harvest or a bad harvest? Will there be disease in the land, or will people be well? Will there be war or peace? Those are the big issues that the gods dealt with. The idea that the gods might care about ordinary people like us, that doesn't begin to pop up until around 400 or so BCE. So we have a few dozen surviving Babylonian horoscopes written for ordinary people. Around the 2nd century BCE, the Greeks get hold of this stuff along with Babylonian astronomy. And the Greeks were already receptive to divination. They had ways of divining the future by going to the oracle at Delphi or by the direction of the flight of birds. So this is just a different way to do it. And in the philosophical school of the Stoics, you have a school of philosophy that's very receptive to the possibility of divination. The Stoics believed in a kind of unity of the cosmos, that there was a kind of sympathy between things in heaven and things on the earth. And that's a general philosophical way of looking at the world that makes you maybe more inclined to accept the possibility of the reality of foretelling the future. We have some hundreds of Greek horoscopes preserved on papyrus. And these are valuable to us because they come to us right out of the sands of Egypt. Papyrus is pretty indestructible as long as it doesn't get wet. So here in these papyrus horoscopes, you have a glimpse into the way prognostication was actually done. We have also half a dozen surviving manuals of astrology, teaching the art in Greek and Latin, and also there are hundreds of horoscopes preserved in those as examples. But the most valuable ones, again, come right out of the ground. I just need to give you a speedy introduction to astrological doctrine. I always insert that I'm not myself a believer in astrology, but it's important to know something about it. To leave it completely out of the picture would be as bad as leaving out Greek religion or philosophy. It's part of the worldview of the day. And in antiquity, there was a debate over the validity of astrology. The great majority of people believed in it, but there were other people who wrote against it. For example, Cicero in his book Against Divination of All Kinds, Sextus Empiricus. So there are opponents of astrology, but there are a small number of them. The fact that they bothered to write about it shows that they felt they were combating something that was pretty pervasive. So basically, each of the planets has particular qualities. It could be heating or cooling. And here I'm using modern astronomical symbols for the planets, but some of them have roots in ancient symbolism too. So that's for the hot ones, that's the sun, the moon, Venus, Jupiter, and Mars. The cooling is Saturn. Mercury is always the astrologer's wild card, so it can be hot or cold. Humidifying or drying. Humidifying planets are the moon, Venus, Jupiter. Drying, the sun, Saturn, Mars. Changeable, Mercury. And so when you add these up, the ones that are overall beneficent, helpful to you, are the ones that are both heating and humidifying. And the destructive ones are Mars and Saturn. So this stuff comes out of Greek medical theory. These 4 qualities are also associated with the 4 humors of the body: blood, black and yellow bile, and phlegm, and so on, and from Aristotle's element theory. But the overall balance between the beneficent and maleficent planets agrees with the Babylonian example. So here the Greeks have taken Babylonian astrology, but found a way to work it into their worldview by attaching it to some trappings of Greek philosophy of nature. Okay, so each planet can be destructive or helpful, but their powers wax and wane as they move around the zodiac. So each planet has a solar and a lunar house. So when Mars is in Scorpio, it would be even more powerful if it's in one of its own houses. Each planet also has an exaltation, a zodiac sign in which its power is increased. You can see the sun is exalted in Aries at the spring equinox. And then the opposite sign is the depression of the planet. So that's already pretty bad. Each planet has powers to get bigger or stronger as it goes around the zodiac. But the planets also interact with each other. So if a planet is in trine aspect, 120 degrees from some other planet, they will reinforce each other. If they're in sextile aspect, only 2 zodiac signs apart, they'll fight. So you got to worry about their interactions as well as their strengths and the way those get bigger or stronger at different parts of the zodiac. And now all these bits I've shown you before have prior examples in Babylonian astrology. Here's something that so far as we know is Greek. Each of the planets actually gets stronger or weaker in the course of the day as it rises, reaches its maximum height or sets. And these are what the Greeks call the places. So the most important place is what's called the horoscope, the place, the hour mark, the place in the east. So when a planet is rising, it will be even stronger. At the midheaven, it's also strong. It's weak when it's setting. So now it's really complicated. You've got to worry about which sign each planet it is in, how they interact with each other, where they are in the course of the day. So there's some great mysteries involving the papyrus horoscopes. For the most part, there are no prognostications. In some of the deluxe horoscopes there are, but in the basic ones, they're just a list of the date, maybe the name of the client, the birth date of the client, where the planets were in the zodiac signs. So usually there are no prognostications and there are no diagrams. How could you possibly do this? You have to think about all this stuff. And the resolution of this is that most astrological consultation was done face-to-face with the astrologer, perhaps in a temple of Serapis or someplace like that. And the astrologer had a board with the zodiac and then stones engraved with the individual planets that could be put down in the correct zodiac signs. So you could visualize the arrangement. And then you would give your interpretation orally to the client. It'd be like meeting with your psychotherapist or priest or rabbi or something, face-to-face and kind of interactive. There is a half a dozen or so novels that survive from Greek times. And one of them is what's called the Alexander Romance. It's a fictionalized account of the life of Alexander the Great. And the oldest surviving stuff comes from around the 3rd century of our era, but the story goes back older. And in the story, Nectanebo, who's the last reigning pharaoh of Egypt, realizes that his country is going to be overrun by the Persians, and he flees to the court of Philip of Macedon. And in the story, Nectanebo tricks Olympias, the wife of Philip, and has an affair with her. And a lot of people don't know this. According to the story, it's actually Nectanebo who was the father of Alexander. It's a pretty juicy novel. In the story, Nectanebo cast a horoscope for the queen. And this is the passage in which that takes place. So while he said these things, that's Nectanebo, he brought out a princely and costly board made of ivory, ebony, gold, and silver, engraved with the zones, having 36 decans. Each zodiac sign is divided into 3 parts, and then 12 signs of the zodiac. And he opened a box and poured out 7 stars in the horoscope made of artfully worked stones. And Venus's stone, or Aphrodite's stone, is supposed to be blue of lapis lazuli. So you might think this was, it's just in a novel, maybe it's just a story, but such objects have actually been found. In the 1970s, an excavation in eastern France, this was brought up from a well. It had been broken into pieces and thrown down in the well. Somebody was upset by astrology. So it answers pretty well to the description by the author of the Alexander Romance. It's ivory diptych. It's about this size. It folds, so there's 1/2 of the zodiac on each side. You can see that there are little bits of gold where the stars were represented. You can see it's divided to the inner ring of zodiac signs and the outer ring, each sign divided into 3 decans. So this is the kind of object that you would use if you were having a astrological consultation. There are a couple of other such boards. These are nice examples of the kinds of objects that would have been used as the planetary markers. Here's 2 stones of Aphrodite. They're of lapis lazuli, as we're told in the Alexander Romance. She's shown coming up out of the water, wringing out her hair, like in the painting by Botticelli, right? The Birth of Venus, 2,000 years later. Stones for Helios and Selene, the moon. And I would like to close with just a few remarks about the use of astronomical objects as signs and symbols. We looked a lot at sundials, and I mentioned the Tower of the Winds in Athens, but here it is today. It's an 8-sided building from the 1st century BC, and around the outside are 8 sundials, each represented by a carefully made dial. Each dial has to be designed separately, facing in a different direction. And then up above, the relief sculpture that represents the personified wind god that we talked about earlier. And we think from some of the channels engraved on the interior floor that there was also a water clock inside. It would have been one of these anaphoric clocks, engraved with the figures of the zodiac that turned around once in 24 hours. So this is not something you need for practical purposes, right? 8 sundials and a water clock. It's a bit over the top. And Vitruvius tells us at the top there was also a weather vane which turned to point and show you which wind god was blowing at the time. In Rome, there's an obelisk which originally came from Heliopolis in Egypt, but Augustus had it brought back to Rome and set up in a square. It's been moved about 200 feet from where it was in the old days. but originally Augustus had it adapted to function as a gnomon. It's engraved with the original Egyptian hieroglyphics, but around the base was an inscription in Latin telling the Romans that he had conquered Egypt and brought Egypt into the empire. So a bit of political imperial propaganda. And remains of the meridian on which the gnomon shadow would fall still survive. You can see them if you go down. You have to go down into the lower level of a cafe, and there they are. They were excavated only in the 1980s, I think, and you can see that it was engraved in Greek. So here's a trilingual monument in Egyptian hieroglyphics, Latin and Greek. Greek for the scientific parts. This one says the Etesian winds start to blow. So this was not a complete sundial, but just the meridian, but it was divided so that you could see which zodiac sign the sun is in when the shadow comes to the meridian at the middle of the day. And there are a certain number of weather predictions, like the commencement of the Etesian winds. Lots of examples of the use of astronomy and astrological symbolism on coins. Here's a coin from Greek Egypt where Queen Berenike shows a cornucopia on the reverse of the coin to remind her citizens that she's the source of the material welfare. But you can see the eight rayed stars on each side to connect her with the celestial realm. A fine bit of imperial propaganda. After the assassination of Caesar, of course, there was a period of warfare among his former followers about who was going to take over. And when Augustus finally went out, one of the coins he had minted was this silver coin showing a comet, which appeared during Caesar's, the funeral games to commemorate his death. And this was supposed to be the soul of Julius gone up to take its place among the gods. So you could see the inscription says Divus Julius, the deified Julius, and there's the eight rayed star and the comet. And finally, a gold coin from the reign of Augustus, and on the back is his zodiac sign. You can see the figure of the Capricorn kind of handling the whole globe of the world. The globe is used as an image, a kind of symbol of the empire itself. And there's also a rudder, which was the symbol of the horoscope, right? The zodiac sign that's rising at your moment of birth. Hoiax is the Greek word for a zodiac. So you can see the number of manifestations of astronomy and astrological stuff in everyday life. It's enormous. It's a rich subject, and we've only just skimmed the surface. But I will stop here and be happy to take any questions you might have.
Thank you, Jim. That's really fascinating, wonderful stuff. I think what it says to me is that whilst we've obviously become much more technologically advanced in the millennia, we're not cleverer than those people. They were doing quite extraordinary things. Remember your geometry from school.
I think there was a question back here.
Hopefully not a basic question, but I'm just interested to understand how accurately the Greeks understood celestial mechanics, so heliocentric, etc. Earth rotation in the day. I mean, obviously you can get some of the stuff from just observing the sky, but did they understand those mechanics?
Well, they had their own physics, which regarded uniform circular motion as the most proper to divine beings. So it would be geocentric. But in the Almagest, Ptolemy gives quite a number of arguments for why you know the Earth is at rest and it can't be moving. He ties it to the physics of the day. He mentions, for example, that if the Earth were spinning, the clouds and the birds would be left behind, and so on. So people do realize that you can't tell by looking whether the Earth is moving whether the Earth is rotating on its axis or the sky is going in the opposite direction. So it was something that couldn't be proven one way or the other by observation. You had to tie it on your philosophy of nature, or what we would call physics. And so once you have that out of the way, most of the rest of the stuff just depends on making good observations. It's easy to time how long it takes each planet to go around the zodiac, for example. And then you could begin to construct a mathematical model to account for the details of the motion. So they get quite far with it. They have a theory which works in detail and with pretty good accuracy, even though we would reject the Earth-centered premise and the uniform motion part of it.
Thank you very much for your talk.
Thank you.
I was interested to try and understand how much of the material and the technology was invented by the Greeks and the Romans themselves, and how much they sort of inherited from the Babylonians and the Egyptians.
A number of different cultures began their own mathematics. We know that the ancient Babylonians were aware of Pythagoras' theorem, even though they didn't have a mathematical proof. And they have sets of numbers that are Pythagorean triples. So there are roots of Greek mathematics in other cultures, but the mathematics is carried to a whole new level and more sophisticated way of doing things with the idea of a structured geometrical proof. For astronomy, the Babylonian knowledge was crucial. It's the Greeks were at the beginning, proving theorems, arguing about whether everything's made of water or whether there's earth, air, water, and fire. So arguing about philosophy, proving mathematical theorems and so on. But the idea that you might need to make consistent observations over generations and keep them and do something with them, that really only comes from Babylonia, because there was a social reason, because it was believed that the gods sent messages to the king. And there was a class of civil servants, the priests in the temples, who kept regular diaries, astronomical diaries, week by week, month by month, year by year, describing the celestial phenomena. So you only need a few generations of such data before you can start making predictions pretty accurately. The observations don't have to be super precise. It's more important to have a long run of them. And then they had a technology, the clay tablet, which is for inscribing the results of the observations. And these were recopied when they were broken. And you've got a place to store them, the temple. So all of this stuff, the social reason to do astronomy, the technology, the class of civil service workers who, and the priests in the temples who make the observations and keep the data, all of that stuff was absent in the Greek world until we get to the period of the big Hellenistic kingdoms. So the Greeks borrow a lot from the Babylonians, and they knew they'd borrowed some, but they forgot how much, and they tend to take credit for things that they weren't really first with. They carried it further, made it their own, and so on. But the Babylonian example was really crucial to the whole development.
Any more questions? No. Pat, no questions online? No. Okay, thanks. We're a bit over time, so I think I'll draw it to a close there. Can we thank Jim once again for a truly fascinating talk?
Thank you all. And I'll be around for a while. I'd be happy if there are people who have private questions. I'd be happy to deal with those too.
Anything you're too embarrassed to ask in public. The next talk is on the 15th of May, and it will be Dr. Shari Breen talking to us about the Square Kilometre Array Observatory. So hope to see you all there. Okay, bye.